All right, this table right here is a really great summary of all of the ways, all the techniques that we have right now for factoring a polynomial. Starting off right at the beginning, factoring out the GCF. I always call that step one. Always start there. Look for a GCF and try to factor it out. If there is one, great, do it, and then continue factoring. If not, fine, continue factoring. They give you an example over here. In this polynomial, the GCF would be 5x squared. So they factored it out, and then they wrote down that. And then from here, we would continue factoring if that was able to be factored, which I think actually it is. Anyway, then, if GCF doesn't work, or if you get yourself down to this situation right here, next would be checking quadratic trinomials. This doesn't mean perfect squares. It doesn't mean shortcuts. It means if I have a trinomial sitting here, factor it. See if it factors. In this particular case, you'd have to use the box method because of this a that's not 1 on that x squared. After using the box method, we would get down to these two factors right here, and then we'd be done factoring. Another method that we have is checking for perfect square trinomials. There's usually going to be some sort of clue that you have perfect square trinomials. In fact, there has to be a clue. You're going to see perfect squares. You'll see a 25 or a 36 or a 49 or some other perfect square sitting there, and that lead term will also be a perfect square. That's your clue that maybe you're dealing with perfect square trinomials, and maybe then you can use the shortcut. If you don't see perfect square trinomials, this method right here will still get you to the answer. So this one doesn't even need to be used at all. It's nice to know it because it can be a time saver, especially unlike the ACT where they typically will throw stuff like that at you. We also have this as our shortcut here. Technically, you could factor it like you were doing up here, but it's best in this case to know that shortcut instantly because you can instantly go from the difference of squares to the factored form, which is conjugates. That one's a fast one that you should know. So in this case, 4x squared minus 15. Technically, 15 is not a perfect square. But I can pretend that's a perfect square by taking the square root of 15 and getting the square root of 15. So in this example, I can actually factor this using the difference of squares by making conjugates and saying that the square root of 4x squared is 2x and the square root of 15 is just the square root of 15. And now I have 2x plus the square root of 15 times 2x minus the square root of 15. This one is a very valuable tool for if you are trying to factor it anyway, even though it's not technically a perfect square sitting there. All right, we also have the sum of squares, which technically isn't really factoring. We're just tricking the math into letting us factor it like the difference of squares, but that would be using complex conjugates, and we talked about that one last time. Factoring by grouping, something that we did extensively or more extensively in Algebra 1. Factoring by grouping is when you have 4 or more terms. Usually it's 4 terms, and you group. So in this case, we'd group the terms that have A's in them and the terms that have B's in them. Then within the groups, we'd factor out the GCF. So the GCF in this guy would be A, which gives us A out front times the x plus y. In this one, we factor out the GCF, in this case is B, which gives us B out front times the x plus y. And then within these two terms, we have A times x plus y plus B times x plus y, which makes this a GCF of these two outer big terms that we have, which means we can pull the x plus y out front completely and write what's left over. So then you'd have the x plus y out front times what's left over in this term, which is A. So open up parentheses and write what's left over, just like you do with any other GCF. In that first term, the A was left over, plus in that last term, the B was left over. And that's how you wind up factoring something that looks like that, by grouping. This is exactly the same answer, it's just that they've written the x plus y at the end and the a plus b in the beginning. You have an example over here of factoring by grouping. In this case, they factored by grouping by doing this. You change the minus sign there to a plus to avoid the sign mistake. And then you factor out the negative, or you put the negative inside the parentheses. And then you're going to do GCF here, which is x squared, GCF here, which is the negative 3, which leaves you with x plus 2 inside the parentheses here and here, so that you factor that x plus 2 out, and then you write down what's left over once you factored that out. What's left over here is the x squared, what's left over here is the negative 3, which gives you that as your answer. It does pop up, so it's good to know how to factor by grouping. If you got 4 terms, that's usually your sign that you're going to be factoring by grouping. And finally, the last one that we just learned, the sum or difference of cubes. You need to know that one, like by heart. Remember the pattern? We have plus minus plus for the sum of cubes, or minus plus plus for the difference of cubes, the sign pattern. And then the number pattern is what number times itself 3 times gives me x cubed, or a cubed, or whatever it is. That goes there. What number times itself 3 times gives me this guy cubed. That number goes there. And then this guy is the square of that guy. This guy is the square of that guy. Take these 2 numbers, multiply them together, put them there, and you're done. The example over here is a good example. 8x to the third plus 1 factors. It's the sum of cubes. So my signs will be plus in the binomial and then minus plus in the trinomial. What number times itself 3 times gives me 8? 2. What number times itself 3 times gives me x to the third? X. So therefore, 2x times itself 3 times gives me 8x to the third. So I write 2x there. What number times itself 3 times gives me 1? 1. So I write a 1 there. And then I go 2x squared is 4x squared, so I write that there. 1 squared is 1, so I write that right there. And then 2x times 1 is 2x, so I put that right there. And I'm done factoring, because that's the pattern. So let's get into some practice problems. We have x to the third minus 27. The question is this the difference of 2 perfect cubes? Yes. Actually, what would be probably helpful is if we made a list of perfect cubes. Our first one would be 1 times 1 times 1, which is 1. And then 2 times 2 times 2, which is 8. And then 3 times 3 times 3, which is 27. 4 times 4 times 4, which is 64. 5 times 5 times 5, which is, 125. And then let's get 6 times 6 times 6 also. Six times 6 is 36. 36 times 6, 216. ACT is probably going to ask you mostly those, if they show up. Anything beyond that is going to be kind of tricky. There are more, like 10 times 10 times 10, some of the more common ones. 10 times 10 times 10 is 1,000. And there are some others that pop up from time to time that are more common than like 7 times 7 times 7. If you want to know what those are, just do that on your calculator and learn them. Make a whole list all the way out to 20 so that maybe you recognize them when you see them. Anyway, is x to the third a perfect cube? Yes. Is 27 a perfect cube? Yes. So we're ready to factor this using the sum or difference of cubes. In this case, it's the difference. So what I recommend you do is, once you're about to try to factor this, set up the binomial times the trinomial. You know it's going to look like that. Then put the signs in there correctly. In this case, we have the difference of cubes, which means that the sign here is going to be minus. There's only one minus sign in these problems, so because I've used the minus there, that one's a plus, and this one here is always a plus. So now I have all my signs in there. All I got to do now is figure out my numbers. The number that times itself gives me this one goes here. So what times itself 3 times gives me x to the third? X. What times itself 3 times gives me 27? 3. The hardest part of what we're doing on these problems is now done. To get this one, I square this one. So what is x squared? x squared. What is 3 squared? That gives me that one. 9. And then I take these two numbers and I multiply them together and I get 3x. And that goes there. That's it. Are you a fan of putting your shoes on and taking them back off before you go outside? No? No. Put your shoes on and leave them on and then go outside. What you're asking me is, do I need to distribute this back out? No. The point was to factor it. If I were to distribute this back out, what would I get? Hopefully. Exactly what I started with. Okay? Put your shoes on, take them back off. Don't. Just put them on and then go on to the next problem. Okay? All right. Next one. Is y to the third a perfect cube? Is 8 a perfect cube? And so we have the sum of cubes. So therefore, we're going to be able to factor this into a binomial times a trinomial. I need to figure out my signs. Plus, minus, plus. It's plus because of the plus here, and then I'd have to have a minus sign in there somewhere. This one's always positive. What will go here? Y. What will go here? 2. What will go here? Y squared. What will go in the middle? 2y. What goes here? 4. And you're done. So see if you can do the last two. Can this be factored? Yes. Into a binomial times a trinomial. Signs are good. What goes here? 2x here and here. So it's this guy squared. 2 squared is 4. X squared is x squared. So 4x squared. What goes here? 2x, because 2x times 1 is 2x, and what goes here? 1. And the last one, are we dealing with sum or difference of cubes here? I think I heard a no. Was there a no out there? Is 27 a perfect cube? Is z to the third a perfect cube? So therefore, is this a perfect cube? Okay. Is 8 a perfect cube? And is x to the third a perfect cube? Yes. So therefore, is this a perfect cube? Yes. Okay. So therefore, this is the difference of cubes. So therefore, we're going to factor it into binomial times trinomial. Minus here. Plus plus. What is going to go here? 3z. What goes here? 2x. So that will be 9z squared. This will be, multiply them together. 3 times 2 is 6. X times z is xz. And the last one? X squared. The whole thing gets squared. So the 2 turns into a 4, the x turns into an x squared. And that's how you factor sums and differences of cubes. Patterns. So we needed another trick, as if we didn't have enough tricks. There's another one that we can use for polynomials that have a degree of 4, 2, and 0. Actually, anything that has a degree of 2, 1, and 0, but then if I take those degrees and multiply them all by any constant number, so like if I multiply them by 2, from 2, 1, and 0, I'd wind up with 4, 2, and 0. If I multiplied those degrees by 3, I'd wind up with 6, 3, and 0. Anytime I have the 2, 1, 0 situation with the degrees multiplied by a constant, then I can use what we're about to use here. That's kind of down the road. For now, you need to know that if I'm dealing with a trinomial, so it has to be a trinomial, and it has to have degrees 4, 2, and 0 on the 3 terms. If that's the case, then what I can do is this process that I'm about to show you here. you can define some new variable to represent the original variable with a degree of 2. And typically we use the letter u. So for this problem, notice that we have x to the 4th, x squared, and then a degree of 0 on this term. That means I can use this process here. How many solutions would I be expecting on this problem? 4. I need 4 solutions. So what I can do is, first of all, move everything over so that I have equals 0. So x to the 4th minus 3x squared minus 4 equals 0. I don't know how to factor a trinomial with a degree of 4. But I do know how to factor a trinomial with a degree of 2. So what I'm going to do is I'm going to say I'm defining some new variable here, let u equal x squared. If u is equal to x squared, then what is u squared equal to? X to the 4th. So I'm going to write that down on this one too. So u squared equals x to the 4th. That means then, so let u equal x squared, then u squared equals x to the 4th. And if that's the case, then I can substitute those letters in. Now I have, instead of x to the 4th, I have u squared. Because u squared is x to the 4th. Instead of minus 3x squared, I have minus 3u. And then the minus 4 equals 0. Now that I've done that substitution, this is the type of problem that I do know how to factor. In this case, I'm looking for two numbers that multiply to give me negative 4, but add to give me a negative 3. Are there two numbers that do that? Negative 4 and positive 1. So now I can factor this into u minus 4 times u minus, or plus 1, sorry, equals 0. And then I can solve for u. So zero product property now. U minus 4 equals 0. U plus 1 equals 0. So u equals 4. U equals 1. Plus. Sorry, I don't know why I keep doing that. So u equals negative 1. Now that I have those two answers, I know that u is equal to 4. But u originally was what? X squared. So I can back substitute now. I can say, well, u was x squared, and u is equal to 4, so that means that x squared must be equal to 4. Over here, u is equal to negative 1, but u is x squared, so therefore x squared equals negative 1. And now I can solve just using the square root property. I square root both sides here, and that gives me x equals what? Plus or minus 2. Over here, I square root both sides, and I get x equals what? Plus or minus I. The square root of negative 1 is I. How many solutions did I just find? 4 total. How many was I looking for? 4. Okay, so this u substitution thing that we just did allows us to make the problem simpler, and then we can back substitute in for x squared and then use the square root property to easily come up with the two solutions out here and the two solutions here. So this is a method that you can use, but only if you have degree 4, 2, and 0 on your 3 terms. If you don't, then you can't use this method. So let's take a look at the second one. What should I do first, probably, if I want to solve for x? Everything on one side. Is it going to be better to move the 27 over here or all the other stuff over there? All the other stuff. So I move the x to the 4th over, plus 12x squared, plus 27 equals 0. Notice that I do have that form. X to the 4th, x squared, and then the constant. The degree is 4, 2, and 0. So I can do my u substitution. So what should I write? Let u equal x squared. As soon as I do that, then this turns into what? U squared. Plus 12u plus 27 equals 0. So now I try to factor it like that. Two numbers that multiply give me 27, but add to give me 12. 9 and 3? Okay. So this is now u plus 9 times u plus 3 equals 0. Now what? Zero product property, u plus 9 equals 0, u plus 3 equals 0. Solve for u. U equals negative 9, u equals negative 3. Back substitute, u is x squared, so I can write x squared equals negative 9, x squared equals negative 3. Square root both sides. So for this one I get x equals, plus or minus, don't forget, 3i is correct. Square root both sides, and I get x equals, plus or minus, root 3i, or I can write it as I root 3. And that's how I'm going to do it, because I don't want to get confused with that I. So I'll write it out front. How many solutions did I get? 4. Okay? Go ahead and try this third one. What do we do? Everything on one side? Now what? U is now x squared. Now what? Substitute in, so we write u squared plus 4u minus 12 equals 0. Now what? Factor. Okay. Two numbers that multiply to give me negative 12, but add to give me 4. 6 and negative 2. So we have u plus 6 times u minus 2 equals 0. Now what? Zero product property. U plus 6 equals 0. U minus 2 equals 0. Therefore, u minus 6, or u equals negative 6, and u equals positive 2. So x squared equals negative 6. X squared equals 2. Square root both sides, and we get x equals plus or minus I root 6. Over here, square root both sides, and we get x equals plus or minus square root 2. 4 answers. We got all of them. So for this last one, again, get everything on the same side. X to the 4th minus 12, x squared minus 64 equals 0. I have the quadratic form. Recognize that it's the quadratic form. It's a trinomial with a 4th degree, 2nd degree, 0 degree. So that means I can let u equal x squared, which means that x, or u squared, is x to the 4th. So therefore I have u squared minus 12u minus 64 equals 0. Now what? Two numbers that multiply to give me that and add to give me that. Numbers that multiply to give me 64. (16 times 4 is 64. And those do add to give me the negative 12 if I make the right signs. So what signs do I need? U minus 16, U plus 4. That does it. So now zero product property, U minus 16 equals 0, U plus 4 equals 0. Solve for U. U equals 16, U equals negative 4. Back substitute in the x squared for u, so we have x squared equals 16, and x squared equals negative 4. Square root both sides, and we get x equals plus or minus 4. And on this one, we get x equals plus or minus. The square root of 4 is 2. But I have that negative inside, so it's plus or minus 2i. So let's take a look at these 4 polynomials that we're looking at here that we found solutions for. The solutions are where the graph crosses the x-axis. So how many times does this graph, this first one right here, cross the x-axis?
4 times.
It has 4 solutions, but how many times does it cross the x-axis? Twice. Why only twice? Because imaginary solutions don't exist. They don't cross the x-axis. It has 4 solutions, but only 2 of them are real, which means only 2 of them cross the x-axis. How about on this one? How many solutions do we have that actually cross the x-axis? None. So this is a 4th degree polynomial that does not cross the x-axis. This one is a 4th degree polynomial that does cross the x-axis, but it does something like that. How many solutions do we have that cross the x-axis on this one? Just 2. And again, this would be a polynomial that crosses the x-axis, and we'll do something like that. And how many solutions do we have on this one that cross the x-axis? We actually only have 2. There are 4 solutions, but only 2 of them are real, which means only twice does this polynomial cross the x-axis. The next thing we have to do is finding real roots by graphing. This is kind of a nice part of the section. There's 2 ways to solve these types of problems. The first is, they're going to give you can think of the equation that you're given as 2 separate equations that have been set equal to each other. So it's like if I had y equals x to the 3rd plus 5, and also y equals 4x squared plus x. And then I set those equations equal to each other, which means I graph this one and I graph this one separately, and then I find where those 2 equations cross. That's what solve by graphing 2 separate equations means. So what I would have to do on a problem like that is look at where the graphs cross, and that's just going to be taking the x coordinates. You'll have 2 graphs. They'll cross. I'll find where they cross using the command on the calculator intersection, and I'll only be concerned about the x coordinates. The other method that we have is solve by collecting terms on one side, and that's what we've been doing. We would move these guys over here and graph all of that as one polynomial. If you do it this way, you're finding where the graph, because now it's only one graph, crosses the x-axis. And then again, you'd just be using the x coordinates. The y coordinate in that case would be 0. And the polynomial on this one would be x to the 3rd minus 4x squared minus x plus 5. You'd set that into your calculator and then find where it crosses the x-axis. Either way, the best thing to do is to graph these on your calculator. Depending on the method that you choose, you're either going to be looking for the intersection or the zeros. Intersection here, zeros here. And the important thing is all you're finding is the real solutions. Like I just talked about on that previous page, you will not be able to find the imaginary solutions using graphing. In order to find the imaginary solutions, you have to use factoring, quadratic formula. If there are imaginary solutions, eventually you'll have to find them. Maybe not so much in this section, but before the chapter is over, you'll be able to find all solutions, including imaginary ones, even if you couldn't factor it. So, for example, find the real solutions of x to the 3rd plus x squared equals x minus 1. Which method does it sound like is probably the better method? Graphing them separately, or graphing them, moving everything to one side and graphing them, move everything to one side? That's what we've kind of been doing, right? Okay, so let's move everything to one side. I mean, do you guys all agree? Is he the spokesman for the room? I agree. I think that it's easier to do this method here. But you're more than welcome to graph them as two separate equations. So let's move everything to one side. We have x to the third plus x squared minus x plus 1 equals 0. And we're going to graph it. And we're going to find where the graph crosses the x-axis. So that means we need to type all that stuff into our calculators. Yeah, but first you got to type it all in. So x to the third plus x squared minus x plus 1. How many zeros should we have? How many should we have with a third degree polynomial? 3. How many do we have? 1. So we can find that one solution right now. We can force the calculator to find it. What does it look like? Looks like 2, but we don't know for sure. So to find that 0, we're going to go Menu, Analyze Graph, and it's a 0, not an intersection, so we're going 0. Lower bound on the left side, upper bound on the right side, and you can see that it's actually not 2. If this will let me move. It's actually negative 1.84. Then you have a different polynomial entered in. So the 0 here is negative 1.84 comma 0, or x equals negative 1.84. And that is the only real solution to this polynomial. Where what we just did is useful is on problems like this. It says friends Stacy, Una, and Amir were all born on July 4th. So they all have the same birthday, but they're not all the same age. Stacy is 1 year younger than Una. Una is 2 years younger than Amir. And then it tells you on July 4th, 2010, the product of their ages was 2,300 more than the sum of their ages. You are supposed to be able to use all of this information to figure out how old each of them was on that day. To do this problem, we need to set up one variable only. It seems like maybe we need 3 variables, but the best way to do it is with just one variable. And you need to realize which person should be attached to that variable. First of all, it says Stacy is 1 year younger than Una. And then it says Una is 2 years younger than Amir. The person who's involved in both of those is Una. That is the person we need to call X. As soon as we have Una is X, then we can use this information. Stacy is 1 year younger than Una. So therefore Stacy equals X minus 1. Una is 2 years younger than Amir. So therefore Amir is X plus 2. Now it says the product of their ages was 2,300 more than the sum of their ages. So what I need to do is on one side of my equal sign, add up all the ages, and on the other side of my equal sign, multiply all the ages. Okay? But then I have to include this 2,300 more than the sum of their ages. So if this is the product of their ages and this is the sum of their ages, which one's bigger according to this statement? The product is bigger, but I want them to be the same. So where do I need to put that 2,300? With the sum. I find the sum and I add 2,300 to it, and that gives me the product. So that 2,300 is going here. Add up the rest of their ages, and you have X plus the X minus 1. So notice I'm putting that in parentheses. Plus the X plus 2, again in parentheses. So this is one person's age, one person's age, one person's age, plus the 2,300. This is the sum of their ages plus the 2,300, which will give me the product of their ages. To do the product of their ages, all I need to do is multiply all those ages together. So that's X times X minus 1 times X plus 2. On the left side, we have the sum of their ages plus 2,300. On the right side, we have the product of their ages, and that's exactly what that last statement is saying. So now from here, what I would do is simplify this down some. Then I would move this whole thing over to get it all on one side and then graph it. So if I combine all my like terms, I have x, which is 3x. I have negative 1 plus 2, which is positive 1, plus 2,300, which is 2,301. But then I have plus, oh yeah, I already did that. So plus 2,301 equals x times x minus 1 times x plus 2. And now I'm going to do exactly what we just did in the last problem. Get everything on one side and graph it. Okay? All right. So that means I'm going to have 3x plus 2,301 minus this whole thing, because I subtracted it all. So minus x times x minus 1 times x plus 2. I don't need to multiply it out because I'm going to graph it. Remember that when I type this in, I need times there and I need times there. All right, let's enter all this into our calculators and graph it. So I've entered all of that into my calculator. I needed to zoom out some to see where the graph actually crossed the x-axis. I should see it cross. I have a third-degree polynomial, which means I could have up to 3 solutions. I only need one. There's one right there. I don't know exactly what it is because my scale is kind of weird and I can't read it, so I'm going to find the 0, analyze graph, find the 0, lower bound, upper bound. There's my ordered pair. 13, 0. So what does that mean? Una's 13. So then I can use the rest of my equations. We need Amir and Stacy. Stacy was 1 year younger than Una, which means Stacy is 12 and Amir is 15. There's your answers. Way, way faster than trying to solve by hand. Use the calculator to get one of them, and then from that you can get the rest. Let's get this one set up here. What are 3 consecutive integers whose product is 480 more than their sum? 3 consecutive integers. What that means is, like 1, 2, 3, those are consecutive. 8, 9, 10, those are consecutive, okay? We want 3 consecutive integers that follow this right here. The product is 480 more than their sum. So I need to define one variable for all 3 of those integers. X, which means that my next number will be x plus 1, which means that my next number will be x plus 2. Now, the sum of those numbers is going to be 480 less than the product of those numbers. So the sum of these numbers is sitting right here. Add them together. 3, 3x. So 3x plus 3 is the sum of those numbers. 3x plus 3, add on that 480, and that will give you the product. The product is going to be x times x plus 1 times x plus 2. And now we basically have the exact same problem as we had above. Combine like terms here, 3x plus 483. Move this guy over, minus x times x plus 1 times x plus 2. This is all one term, so I just subtract it all. And that's what I get, equals 0. Graph this as is. Find where the graph crosses the x-axis. Where it crosses the x-axis gives you that one, which gives you the next 2 immediately. When you graph it, it will cross the x-axis at 7. Which means that 7, 8, and 9 are our solutions.